additional molecules here. We have nitrogen and we have sulfur in most but not all proteins. I'd like you to know that. What do proteins do? What's the physiology behind proteins? Proteins give your cells structure. I want you to underline that. A lot of times the knee-jerk reaction is when you talk about what the shape of a cell is and you ask somebody what gives a cell its shape, the knee-jerk reaction most times is, what do you think? The phospholipid bilayer. Okay? I ask a student that, what gives a cell its shape? They'll say, well, of course it's a phospholipid bilayer. No. What gives you your shape? Does your skin give you your shape? It's your, what, bones and your muscles. That's what gives you your shape. Your skin covers it. Cells no different. The phospholipid bilayer is just covering the shape of the cell. What gives that cell its shape is the protein underneath it, which makes up the cytoskeleton. You guys know the cytoskeleton is made of proteins, so you can talk to you guys about that. So if I ask you at any time on the exam or whatever, what gives a cell its shape? You don't say fat, you say protein, because it's a cytoskeleton. So that's one thing that protein does, is it gives cell its structure, and the structure of the cell needs to be maintained, by the way. You change the shape of the cell, it doesn't work right. Structure, function. What else do proteins do? They regulate a whole mess of stuff in your body. Every enzyme is a protein. I gave you one enzyme already, ATP synthase, that's protein, makes ATP. Hormones, there's a bunch of hormones in your body that regulate a whole mess of stuff that we'll talk about in excruciating detail next semester. You guys might have already heard about the endocrine exam that comes at the beginning of next semester. We're going to talk about a whole mess of proteins next semester. Hormones. Many of them are proteins. They transport stuff. Hemoglobin, you guys know what hemoglobin is, right? What's hemoglobin mainly transport? Oxygen in your blood. There's a whole bunch of other proteins in your blood that are carrying stuff like cholesterol, LDL, HDL. Part of that molecule is protein. Cholesterol is just piggybacking on that protein. Your immune system is protein. In large part, it's protein. Something called the complement system. Those of you that are taking micro will learn about this in a ton of detail. Antibodies are protein. If you don't have protein, you don't have an immune system. Okay? And again, general homeostasis. So protein does an awful lot of stuff in the body. An incredibly important nutrient. Now when it comes to proteins, I'm going to draw a protein. It's going to look a lot like a polysaccharide, by the way. It's going to look exactly like a polysaccharide. I'm going to draw a bunch of circles. That's a protein. But those circles are obviously not glucose molecules. Those circles are what? What makes up a protein? You guys remember this? I heard it. Amino acids. So those circles are amino acids. You stick amino acids, you stick two amino acids together, you have a protein. It's a little itty bitty protein, and it actually has a special name. So if you have anywhere from about 2 to 10 amino acids stuck together, how many do I have there? 2, 4, 6, 8, I got 9. That protein would be more correctly called a peptide. So if you have 2 to 10 amino acids nested in your nose, it's called a peptide. Can you call a peptide a protein? Will somebody come and smack you if you do that? No. A peptide can be called a protein, but if we wanted to be very correct about it, we would call it peptide. A peptide is a little teeny protein. Anywhere from 11 to roughly 50, and depending on what book or what site you are on the internet, try to stay off the internet, by the way, when it comes to finding out stuff. There's a bunch of crap out there. But this is what I'd like you to know. The general rule is 11 to 50, we now call that a polypeptide. Again, most correctly, can you call a polypeptide a protein? Of course you can. All right? And then once we get beyond 50 amino acids, okay, you don't call it a peptide, you don't really call it a polypeptide, it's a protein. But again, all three of those are proteins. It's just the size is dictating what we would call it most correctly. Okay? Very simple, straightforward. Now, when it comes to protein, what else do we need to know? How it's put together. So each of these circles in this picture are an individual amino acid, and the circles are all different colors. There are 20 different amino acids that make up the proteins in your body. Every protein in your body is produced. So you eat a steak. Steak's got a bunch of protein in it, right? Those same protein molecules do not make it into your blood. What your digestive system does is, it chops them up into amino acids, dipeptides and tripeptides. That would be 2 amino acids and 3 amino acids stuck together. That's what your digestive system does. Chops up the protein, it goes into your blood, those amino acids then go into the cells, and then the cells stick together again. Okay, we'll talk about it next time. Why would the hell would the digestive system do that? Proteins are too big to get into the blood. They need to chop them up. If I had a table that was too big to get into the door, what do I do at the table? I take it apart, I bring it into the room, and then I put it back together again. That's what your body does. The foods that you eat are chopped up into smaller pieces so that they can get into your blood, and then the body utilizes them. So every protein in your body is produced by the cells of your body. And on Wednesday, we'll get into the details of that. It's called transcription and translation, something we guys are talk about, I'm sure. But before we get to that, when we have all these amino acids strung together, they're strung together in a very specific sequence. So we have these different colors. This protein needs these 2 amino acids to be here, and these 3 to be here, and those 2 to be there, and so forth, and so forth, and so forth. They have to be in that order. If they're not, the protein might not work. Okay? So we need to put the amino acids in a specific order, and the amino acid specific order is called something special, or specific. I don't want to say special. That's the primary sequence. All right? Primary sequence means the amino acid sequence. And you can have anywhere from 2 to tens of thousands of amino acids stuck together to make a protein. It depends on the protein. All right? Now, at that particular point in time, that protein's probably not working. So I'm going to give you an analogy. I'm going to take a pearl necklace. I'm going to unclasp the pearl necklace. One day. We're going to imagine that all the pearls are white. They're all different colors. Each pearl is an amino acid. Okay? All different colors. That's primary structure. Now, for this protein to work, to really take on its shape that it needs to be in, what's going to happen is those amino acids, they're going to start to interact with each other. Because some of them have a positive charge here and there, others have negative charges, and then there's parts of the amino acids that don't have any charges. So they're going to start to interact with each other. So I'm going to take that pearl necklace on this side and this side, and I'm just going to kind of give it a twist. Now I'm doing it, I'm twisting the pearl necklace. Okay? There aren't little fingers inside the cells. So there's nothing physically twisting in the primary structured protein at that point. It's the charges that are interacting with each other from one amino acid to the next that's causing it to twist and to kind of pleat. So if we had to draw this, well, what the hell, why don't we? So primary structure, that means primary. I'm just going to put these amino acids and then stick them together. A little short, little protein, okay? We just made a peptide. And then what's going to happen is that, again, those amino acids are going to start to interact with each other. And then, I don't know, let's just draw it like this, do like that. So there's the amino acid, there's one, there's one, there's one, there's one, there's one, there's one, there's one. That's secondary structure. It's starting to take a more globular shape. Not yet though, but it's going to. And so these amino acids are going to continue, let's even put the word interact here. They're going to continue to interact with each other. And as they do, I don't know, just do it. There. That's tertiary structure. It's more globular now. It's not this little straight thing that's kind of twisting here and twisting there. If I took that pearl necklace and I just dropped it in my hand, now that's what that protein looks like. Now when I dropped it in my hand, it randomly arranged. That's not what happens inside of these cells when the protein is being formed. It's not random at all. The formation of that protein, the structure of that protein at that particular point in time is exactly what it's supposed to be. Because the amino acids were put in just the right sequence to begin with so that the interaction was perfect. Okay? So now we have this globular structure. Now, I'm going to put like a hard line here. Because this doesn't always happen. You know, I have the luxury of having different colored pens up here. So I'm going to use different colors. Now what I've just done there is I've made a big structure called quaternary structure made up of tertiary structures. So this is a tertiary structure. So is this one. So is this one. A quaternary structured protein is one in which proteins, smaller proteins, have come together to make a big one. I'll give you a first example of a protein that has quaternary structure, hemoglobin. And we already talked about hemoglobin. They talk about it, but I mentioned it. You guys told me that it carries oxygen in the blood and all those other things. Hemoglobin is actually 4 proteins that came together to make the bigger one. And when we have these individual tertiary structures coming together, each of those is called a subunit. That's in your notes. So that's a subunit now. So is this one. That's a subunit. This particular protein has 3 subunits. Hemoglobin happens to have 4 subunits. Some have 6, some have 8. Got words in the notes. Right here. So quaternary structure, combining of 2 or more tertiary structures. Each individual tertiary structure is now known as a subunit. And now we have a working protein. And so a quaternary structured protein is one that works as a team. Are there tertiary structured proteins that work all by themselves? Yes, many of them. All right? And actually there are proteins that can work at this point right here. What do I want you to know? I want you to know what primary structure is. It's the amino acid sequence. I want you to know that secondary structure is, it's starting to twist a little bit. I want you to know that tertiary structure, now it's glob, you look like you dropped a pearl necklace in your hand. And I want you to know that quaternary structure is tertiaries coming together. What makes them come together, by the way? Stuff that happens inside the cell. Some biochemical things, signaling things that happen. Okay, not important for us to know. All right? Are we good? More later, a lot more later, I promise. Now, what else do we need to know here? I want to mention the word denaturation. As soon as you see the word denaturation, as soon as you see it, you think protein. You think we just changed the shape of a protein. That's what denaturation means. Okay? How do you change the shape of a protein? And by the way, that's not good. You don't want to change the shape of a protein because now it might not work or work well. How do you change the shape of a protein? How do you denature a protein? I have in quotes extreme conditions. Now, why do I have it in quotes? The reason is that it's extreme inside the body, but if we thought about it environmentally, it wouldn't be. I have temperature as an example, pH as an example. The changes are not extreme. If we were chemists, we wouldn't think that these changes were extreme, but we're physiologists in this room. And within the body, it is. So if we had to draw, for example, our homeostatic line for pH, can you give me the range, by the way? You guys remember? What's the normal range? I heard it, 745 to 735. That's our normal range. That's our homeostatic range, right? Let's say we're up here at 8. Or down here at 7. To a chemist, that's pretty much peanuts. That's a 0.35 pH change roughly in either direction, 7.8 or 8. It doesn't matter. It's not a big change. If you are a physician or a PA or whatever, a nurse practitioner, whatever, and you had a patient and you took their blood, their arterial blood, and you saw that they had a pH of 8 or maybe another one had a pH of 7, you would be panic-stricken because they very well might die. Why? Because at this point, they're starting to denature as we get up to that point. They're going to denature like crazy here. Well, what kind of things are we going to denature? What are proteins? Enzymes, hormones, structures of cells. Does that sound good? You got enzymes that don't work, you're screwed. If you don't have hormones that work, you're going to get screwed. You got cells that don't have the name, the shape, you're screwed. Well, you're not screwed, the patient's screwed. You better fix it. Okay? So, when we talk about changing the shape of a protein, it's denaturation. And by the way, when we change that shape, we're not changing the amino acid sequence. We're not changing primary structure. We're changing the interaction of the amino acids. That's what we're doing. We're changing secondary, tertiary, quaternary. We're not changing primary. Can we change primary structure? I'll talk about it on Wednesday. Okay, it's called a genetic mutation. That will change primary structure. and it's in the notes explicitly, I even have it underlined, when it comes to DNA